Okay, so in this video I'm going to start one of the three major theorems in vector calculus, this being Green's theorem. The other two major theorems are Stokes' theorem, which is very similar to Green's theorem, and the divergence theorem, which is also similar to Green's theorem. So basically Green's theorem is a convenient way for someone to avoid doing line integrals. Maybe you have a difficult line integral to compute. Maybe it would be difficult to parameterize the curves. So basically Green's theorem gives you an alternative way to compute a line integral without actually having to compute a line integral. Okay, so I'm going to write down Green's theorem, and then I'm going to do sort of a proof. It's not a very satisfying proof, but it's the proof that you'll see, like if you ever take this in university, this is usually the way they prove Green's theorem. So you'll see what I mean. Most people don't find it very satisfying, but it's generally the proof that people go with. So this is Green's theorem. So the line integral, the closed loop line integral around a curve C. Okay, so that's f dot dr. Rather than computing this line integral and parameterizing the curve to find dr, and then substituting your parameterizations in for the x and y variables in f, Green's theorem says that you can, rather than doing this closed loop line integral, instead you can do a double integral of, I'll write it like this, dA. So sometimes you see it written like this. I don't really like it like that. I'm going to write down all the different forms of Green's theorem. Okay, so here are most of the ways that Green's theorem can be written. There's another way where Green's theorem can be written that looks a lot like the divergence theorem, but I'm not going to bother talking about that yet. So basically, if you look at this line down here at the bottom, let's say that F, the vector field with components P and Q. Okay, so we're just in the plane here. You can see, hopefully, that if you dot this with dr, dr can be written like this. Okay, and then if you abuse the notation a little bit and think of multiplying through by dt, you can see that when you take these two dot products, you have p times dx plus q times dy, which is what I have written here. So these two things are equivalent. And then Green's theorem states that the line integral around the closed curve C is equal to this double integral, where this this thing right here is actually equal to the curl of f. So sometimes that's written like this, dotted with the unit vector in the k hat direction. Okay. I don't think I talked about curl yet, so I'm not going to use this notation here. I think I'll save that until I actually give it a more thorough description. But so right now, the form of Green's theorem that I'm actually going to look at is this guy right here. Okay, so the thing that makes this proof not very satisfying is that you prove this formula sort of part by part, where each part is limited in scope. So the part that I'm gonna prove here is actually limited to this type of region here. Okay, so this is called the type 1 region. Basically, what it is, this is the closed curve C, and basically you break each part of the curve up into these sort of subcurves, and so we have 4 subcurves here, that all added together equal the curve C. And this top curve here, we'll call it y equals u, which is some function of x. And on the bottom here, we'll say that the curve along the bottom here is another function, say u1 of x, and we'll call this one u2. Okay? So C is the curve that encloses the region D, and C comprises of the curves C1, C2, C3, and C4, where C2 is a function of x, and C4 is a function of x. Obviously, C1 and C3 can't be functions of x because they're vertical lines. They're the lines, x equals a and x equals b. So basically, if you can prove that p dx equals, okay, so this is the partial derivative of p with respect to y, which is what I have here. If you can prove this part of the integral, okay, so this term and this term, then it stands to reason that if you can prove that this term equals this term, then there's sums. The sum of these two guys is going to equal the sum of these two guys here. Okay, so usually the way this is done is you prove sort of like this identity, and then you just say similarly the line integral of q dy is going to equal this, and then in that case you would have to use a type 2 region to prove that identity, and a type 1 region to prove this identity here. So that's what I'm going to do. Okay, so let me work on the left-hand side of this equation first. So what would be the closed loop line integral around C be equal to? Well, it would be equal to the line integrals on C1 p dx plus the line integral on C2, the line integral on C3 plus the line integral on C4. Okay, so right off the bat you can see that on C1 and C3 x is fixed. Okay, so x doesn't change on C1 and C3, so that means that on C1 and C3 dx is going to be equal to 0. So right off the bat, C3 and C1, you can get rid of these terms here. Okay, so basically you can show that the closed loop line integral of p dx is going to be equal the integral of p dx along C2 plus the integral of p dx along C4. Okay, so f is a function of x and y. So that means that p is a function of x and y, and q is a function of x and y. Okay, those are the coordinates of this vector field. So this vector field is in this plane like this. Okay, that's f. So that means that we can rewrite these guys as, well, let's look at C. Let's look at C2 since I wrote that one first. So C2 is an integral from b to a line integral from b to a of p dx. Okay, so p is a function of x, and on C2, y is this other function. Y is u2 of x. u2 is a function of x. So I can substitute that in for y inside this p term here, dx. And like I said, it goes from b to a. Similarly, on C4, it's the line integral of pdx from a to b. Okay, so on this curve here, we go from a to b, and p is a function of x and y, and along C4, y is u of 1, or u sub 1 of x. Right, so I plug that in right here. Okay, so I can rewrite that as this. You know from calculus that I can reverse the order of this integral here and put a minus sign out front, and that would be the same integral. Basically, I'm just going in the opposite direction. Okay, so if that were the case, then both integrals would be from a to b. This guy would be the positive one, px u1 of x, and then this integral here would be negative. Okay, so that's as far as we have to go with this guy here. Okay, so here's our result from the left side here. Okay, so we shown what the line integral around c pdx is going to be equal to. It's going to be equal to this guy here. So now, if we can show that this term over here on the right side, if we can show that that term equals this, well then we know that these two terms are equal to each other. And then, like I said, you can use a similar argument over a type 2 region to show that the terms that are left are also equal to each other. Therefore, when you add these two terms together, it's going to be equal to the sum of those two terms there. Okay, so now let's try to prove this part right here. So this is pretty easy. Okay, so I'll write this like this. Okay, this part here is actually really easy to show. Okay, basically you just use the fundamental theorem of calculus. The left-hand side of this equation right here. So what does the fundamental theorem of calculus say? Let's just say that first. If you have some integral f prime of x dx, then this is going to equal to the function evaluated at the two boundary points, right? So here you can see that partial p, partial y, that's sort of like this term. If I know I haven't talked about double integrals, but they're super easy, so I'm not even going to spend any time talking about them. Basically, a double integral like this, you compute the inner integral, and then you compute the outer integral. Okay, so if we just look at the inner integral here, this first integral sign, and we look at partial p, partial y, dy, that's basically what you see right here. Okay, so if you look at our type 1 region, this is why we're using a type, this is another example of why we're using a type 1 region in this case. We're integrating with respect to y. So where does y start and where does y finish? Well, y finishes on C4, or y starts on C4 and goes up to C2. So y goes between u1 of x to u2 of x. Okay. Partial p, remember p is a function of x and y. So after we compute that inner integral, then we have our new integrand for our outer integral. So this is with respect to x, so how does x vary over this region? Well, x goes from a to b. Okay. So now if we just leave the outer integral as it is for now, compute the inner integral, well, what does the fundamental theorem of line integrals, or what does the fundamental theorem of calculus say? That if you have a derivative in here, a derivative with respect to, this is a derivative with respect to x, and we're integrating over dx here. So here we have an integral, or we have a derivative with respect to y, and we're integrating with respect to y. Okay, so what we just end up getting is just p evaluated at the two endpoints. Okay, so we end up with p x u2, just a safe space. I won't put u sub 2 of x here. I'll just leave it like that because I'm running out of space. And evaluate at the other endpoint, u1 dx. Okay, so you should be able to see that these two guys here look a lot alike. The only difference being that when we have u1 substituted here, this is the positive term, and the negative term is when u2 was substituted for y here. So obviously you can see that there's a negative sign here. So if I multiply this integral through by that negative sign, then what do I get? I get exactly what I have here. I have the integral from a to b. Okay, and there we have it. We showed that when we look at just this term here over a type 1 region, we show that this term here is going to be equal to this part of this formula here. Like I said, similarly, you can use a similar argument to show that this term here over a type 2 region is going to be equal to this guy here. So it stands to reason that when you add these two guys together, it's going to be equal to the sum of the results that we got down here over here. Okay, so Green's theorem can be used both ways. Earlier I said that if you have a really nasty line integral to calculate, and it's be difficult to parameterize it, instead you can compute the double integral over the region enclosed by the closed curve. Of this term here, which is just, like I said, it's just the curl of f dotted with k hat. That will make more sense later. For now, you can just take this formula for what it is, and maybe that would be a lot easier than computing the line integral. But conversely, maybe you have a really nasty double integral to calculate over some closed region, and it would be a lot easier to use Green's theorem in reverse, and calculate the line integral around its boundary rather than computing the double integral over the region. Okay, so in the next video I'll go through, I guess, an example of each using Green's theorem in this direction to simplify things, and then maybe again using it in that direction to simplify things. And hopefully you found this proof, this pseudo-proof, somewhat satisfying. I know I don't, but generally this is how it's represented. So, so thanks for watching.